Hello and welcome. This is my second lecture on chapter number 3, that is Markov chains. Okay, and in this video I'll start talking about the long-term properties of a Markov chain. Okay, so the property that we are going to discuss here is stationarity. So the first thing I'm discussing with you guys is the stationary or the invariant distribution of a Markov chain. Okay, let's see what do I mean by that. Okay, when I talk about stationary distribution, the first thing that I need to know is what stationarity is. Okay, so what stationarity meant in chapter number 2, stochastic processes, I had defined stationarity, and it means the same thing for the a Markov chain as well, because a Markov chain is a stochastic process. So stationarity means that the statistical properties of a stochastic process, here it's a Markov chain, okay, of a Markov chain doesn't change as time elapses. Okay, so time is continuously elapsing, okay, but the distribution or the statistical properties of the Markov chain are remaining the same. Okay, so that is what stationarity means, and a lot of Markov chains after a point of time attain their stationary distribution, which means effectively, see, if a Markov chain is going from x0, then it has x1, x2, so on and so forth, and at time t, let's say at time t, it reaches its stationary distribution. Okay, let's say this is the stationary distribution. After this time, the statistical properties, that is the mean, variance and the skewness and everything, will remain the same. Okay, so the statistical properties would remain the same for xt plus 1, for xt plus 2, so on and so forth, right? So the distribution of this Markov chain would remain the same after time t, right? So all of these distributions would effectively be the same. So xt would be equal to xt plus 1, which would be equal to xt plus 2, so on and so forth. So once the Markov chain has attained a stationary distribution, the distribution will continue to remain the same. Okay, so how do we calculate this? How do we go about calculating the stationary distribution of this Markov chain? Okay, so for this to be true, xt plus 1, right, which would be equal to nothing but xt into p, right? Xt plus 1 is a vector here which shows the distribution at time t plus 1, and xt is a vector which shows the distribution of the Markov chain at time t. Okay, so whenever you transition from time t to t plus 1, this thing is my xt plus 1, and this thing should come out to be same as xt. Okay, so I can just express this as the property for the Markov chain, okay, to be stationary. So the distribution at time t, if I multiply it with the Markov chain's transition matrix, right, it would return the same distribution. Okay, and this distribution xt, it is usually referred by the letter pi. Okay, so effectively pi p equal to pi. Here pi is referred to as the stationary distribution of the Markov chain. Okay, so pi, or I can write it as xt. Okay, pi or xt is a row vector representing the stationary distribution for a Markov chain. What this means is that it is a distribution which returns to itself if I multiply it by p, right? It is a distribution that returns itself if I multiply it by p, right? So that is what a stationary distribution is. right? That is what it means. All right. So this is what a stationary distribution is. Now let's take a example. Okay. So let's just consider an example from your study material itself. Okay. So the state space of this process, this Markov chain, is 0 and 1. Okay. So there are only two states, 0 and 1. And the transition matrix is given like this. Okay. So I can even draw the transition diagram. So 0 to 1. The probability of staying in 0 is half, right? Probability of going from 0 to 1 is also half. The probability of coming back from 1 to 0 is 1 by 3, and staying in 1 is 2 by 3, right? So this is what our transition diagram or transition graph look like. Okay, so now we need the stationary distribution of this chain. Okay, so I can write the stationary distribution as pi, right? Pi is the stationary distribution such that pi p is equal to pi. Okay, where pi is equal to, pi is a row vector representing the stationary distribution, right? So it can be written as pi 1 comma pi 2. Okay, it will have two elements, or let's call it pi 0 and pi 1, right? Because I've got two states, 0 and 1. Okay, so pi 0 comma pi 1, right? So this is my stationary distribution, and I want to calculate the value of pi. Okay, I want to calculate this row vector. All right, so let's just do it. So I need pi p is equal to pi, so that would become pi 0 comma pi 1, right, into p. P is half 1 by 3, 2 by 3, right? And this should return the same thing, that is pi again. So if this transitions from one time to the next time, it should return the same distribution, that is pi 0 comma pi 1, right? Now this will give us a few equations. Okay, so let's take down the equations in order to solve this. Okay, so equation number 1 is pi 0 into half plus pi 1 into 1 by 3 is equal to pi 0, right? So I'm multiplying the rows of this with the column of this and then getting the first value. Okay, so this becomes half pi 0 plus 1 by 3 pi 1 is equal to pi 0, right? And the second equation is half pi 0 plus 2 by 3 pi 1 would be equal to the second value, that is pi 1, right? So this is how I can just multiply this. Now I have two equations and I can use these two equations to find the value of pi 0 and pi 1. Okay, but there would be a problem if I do that. Let's see the problem. Okay, so the first equation, it simplifies to, now 1 by 3 pi 1 sending pi 0 to the other side becomes half pi 0. Okay, this is my first equation, and the second equation becomes, if I send the pi 1 to the other side, it becomes half pi 0 is equal to 1 by 3 pi 1. Okay, so both the equations give the same result, and if I solve them now, they both will cancel out and give me nothing, right? So I cannot just solve with the help of these two equations. Okay, so what I need to do is I need to use one more equation. That would be something I know. See, I know that the distribution, okay, the row vector, this row would add up to 1. Okay, because these are probabilities, so the person can either be in state 0 or in state 1. Process can either be in state 0 or in 1. So pi 0 plus pi 1 would be equal to 1, right? Because this is a row vector with mutually exclusive and exhaustive events, right? So this would be equal to 1. Now what I do is I would eliminate one of these equations. Okay, the first two equations, out of these two, I'll eliminate one and take just one. Usually we eliminate the most complicated one, but here both of them are exactly the same. So let's just eliminate the first equation. Okay, so the first equation is not there anymore. Now I have to find the value of pi 0 and pi 1 based on the second and the third equation. Now if I do this, How would I go about doing this? See, from this equation number 2, I can see that if I send this half on the other side, it becomes 2, right? So pi 0 is equal to 2 by 3 pi 1, right? That's something I know now. Okay, now I can substitute this value of pi 0 into this equation, so that becomes 2 by 3 pi 1 plus pi 1 is equal to 1. Now if I add them, it becomes 5 by 3 pi 1 is equal to 1, which would imply that pi 1 is equal to 3 by 5. And since they both add up to 1, pi 0 would be, putting it again into this would give me pi 0 is equals to 2 by 5. Right, so these are my values, and this would give me my stationary distribution. So my stationary distribution becomes 2 by 5 and 3 by 5, right? So this, if I have this distribution, it is a stationary distribution, that is, it will lead back to itself in the next step. So if these are the probabilities of being in state 0 and state 1, it's the probabilities of being in state 0 and 1 in the next turn would be the same as well, right? So okay, so that is how we work out stationary distributions. Let's just take a few more examples, and then we'll see how does a Markov chain attain a stationary distribution, and does it in all cases or not. Okay, so we'll try to see that. Right now I'm just taking three questions to calculate the stationary distribution. So that is my agenda right now. Okay, so let's do that. Okay, so the next example is a complicated one. It is a process which has 5 states. Okay, the states are 0, 1, 2 plus, 2 minus, and 3, and the question says that find the stationary distribution for a chain given by the transition matrix this. If you can recognize it, this is the transformed transition matrix for model 2 which we had discussed, wherein we had 4 states, but we had also added one more state, that is 2 minus, because we wanted to make the process a Markov chain. Okay, so this is that process with the 0%, 25%, 40%, and 60% discount, which wasn't a Markov chain. Okay, in which the falling down a state depended upon the last year's claim. Okay, so we made it Markov, and this was the chain. Okay, and for this now we need to find the transition matrix, right? So first of all, we'll make all our equations. Okay, so let's try to make the equation. Equation number 1 would be, so how will I go about doing the equations? I'll first multiply pi p and make it equal to pi, right? So this would mean that pi 0 comma pi 1 comma pi 2 plus comma pi 2 minus comma pi 3. This thing, this entire thing, this vector would be, if multiplied with this matrix P, okay, it would lead to the same thing. Right, so I'll have to multiply the row of this with the column of this and get these values, right? And that is how I'll go about just doing this question. So I'll get 5 equations here. I did get 2 in the last question. This one I'll get 5. Okay, so the first equation is multiplying this with this and getting the first value, that is pi 0. So it would be 0.25 pi 0. Okay, this first value into this first value, right? Plus 0.25 pi 1. Right, and then you have got 0, and then you have 0.25 into pi 2 minus plus 0.25 into pi 2 minus, and this thing would give and the last value is 0 as well, so the value for this would come out to be pi 0. Makes sense, right? So this is what our transition matrix equation looks like, right? So this is the equation, first equation that defines the stationary distribution. If you check all of these equations, okay, so now we have these equations, and using these equations we'll have to solve for all the values of the pi's. Okay, all the pi j's we'll have to solve. Okay, Okay, now if we solve all of these equations, we have got 5 equations and we have got 5 variables, okay, which we have to calculate the value for. So we have got a system of 5 linear equations. But if we will solve all of them, the answer you'll get for all of them would be 0, because all the equations will cancel out and you won't get any meaningful result. So for this, what we do, we use the normalization property, okay. The normalization property means that the sum of the row vector is equal to 1, right? So pi 0 plus pi 1 plus pi 2 minus plus pi 2 plus pi 3, all of these will add up to 1, okay. So this is called as a normalization property, which we'll have to use in order to solve this system of linear equations, okay. And out of these 6 equations, we'll have to delete one of the equations now, okay. So the equation that we'll delete would be the most complicated one. I would prefer it to be that one. So I can delete either one from 1 or 5, okay. Let's say I consider deleting 5. So I'm removing the 5th equation and taking into account the 6th equation now, okay. So now the best method to solve this set of 5 equations, 1, 2, 3, 4 and 6, is to decide upon a working variable, okay. The working variable would be, it could be any one of these, and what I mean by the working variable is that I would express all of the other variables in terms of that variable. So let's say I decide to take pi 1 as the working variable. So now I need to express each one of the pi's in terms of pi 1, right? So first equation that I have is pi 2 plus is equal to 0.75 pi 1. So this is how I can express pi 2 plus, right? Pi 2 plus is equal to 0.75 pi 1. This is one equation that you have. Now let's try to express pi 0 in terms of pi 1 from this one. So pi 0 is equal to, I know the value of pi 2 plus already, that's 0.75 pi 1, right? So I can just substitute it here and then get the value of pi 0 in terms of pi 1, right? So let's do that. So that would give me pi 0 is equal to pi 1 minus 0.25 into 0.75 pi 1, right? I've just sent this pi 2 on the other side and substituted it with this equation, and then I will say that the coefficient of pi 0 was equal to was 0.75, right? So I'll divide this entire thing by 0.75, right? So this is how I can express pi 0 in terms of pi 1, and this would give me the value of pi 0 from here would come out to be 13 upon 12 pi 1, right? So I have got this to be equal to 13 upon 12 pi 1. Pi 0 is equal to this. Now I need to express pi 2 in terms of pi 1, pi 2 minus, and then I need to express pi 3, right? Let's try with pi 2 minus. So if you solve this equation here, okay, you can express pi 2 minus in terms of pi 1. Pi 2 minus would be equal to, if I send everything on the other side and express it in terms of pi 1, it would come out to be 9 by 4 pi 1. Okay, you can try this. You'll have to substitute the value of pi 0 here and here as this value. You'll have to substitute it as 13 by 12 pi 1, and then if you send everything on the other side, you'll get pi 2 minus is equal to 9 by 4 pi 1, right? And now from the last equation, I can get the value of pi 3 as well. So pi 3 would be equal to pi 2 minus divided by 0.25, right? Which would give me pi 3 being equal to 9 pi 1, right? So these would be all the values that I will have, right? These would be all the values. So I have expressed everything effectively in terms of pi 1. Now I can use the normalization property to find my answer. I can add all of them up and equate them to 1, right? So I can write that pi 0, I'll write all of them in terms of pi 1, right? So pi 1 is 1 pi 1, right? I can write this as pi 1. Pi 0 is equal to 13 upon 12 pi 1. Then pi 2 minus can be written as 9 by 4 pi 1. Then pi 2 plus can be written as 0.75 pi 1. And finally this pi 3 can be written as 9 pi 1. Okay, and this I would equate with 0, which would give me pi 1 being equal to 1 upon 0.75 plus 1 plus 13 by 12 plus 9 by 4 and 9, right? So this would give me my pi 1, which would be equal to 12 upon 169. Okay, and now I can calculate the value of all the variables. Okay, so my pi 0 would be equal to 13 by 12 into 12 upon 169, which would be equal to 13 upon 169, or 1 by 13, whatever you want to write it as. Pi 1 would be equal to 12 upon 169. Pi 2 plus would be equal to 9 upon 169. Pi 2 minus would be equal to 27 upon 169. And finally my value for pi 3 would be equal to 108 point divided by 169. So now I can just write my vector for pi, that is my stationary distribution, and it would be equal to 13 upon 169 and 12 upon 169, 9 upon 169, 27 upon 169, and finally last 108 point divided by 169, right? So this would be my value for the stationary distribution, and this is how you solve it. Okay, so the steps are, the first thing that you have to do is you need to eliminate one of the equations, then you need to introduce the normalization property, and then you need to select a working variable, express all the other variables in terms of that working variable, and then solve for that working variable and find out the value for all the other variables. Okay, now so let's just take a note of a few things. The first thing that is that if a Markov chain attains its stationary distribution at some time t, for all the times n that are greater than t, okay, the distribution or the statistical properties remain stationary or same. So once a stationary distribution is attained, every time you will multiply that stationary distribution with the probability matrix, with the transition matrix, you would get the same stationary distribution, so the statistical properties would stay the same. This means that once a Markov chain transitions into its stationary state, it tends to stay stationary forever, right? So once it's stuck there, it will keep on staying there, right? That is the idea here, right? The next thing is the procedure for finding a stationary distribution that we have already discussed. I've listed it in form of a few steps. So step 1 is that we have to apply pi p is equal to pi, the property, and then we'll have to get a system of linear equations, right? So we'll have a couple of equations here, and then the next thing is to eliminate the equation which is the most complex one. You can eliminate any equation, but it is preferable to eliminate the most complex one, right? The next step is to apply the normalization property. That means that the sum of the row vector for all the values of j adds up to 1, right? So I'll add all the values of the row vector. So I'll add all the pi values, pi j values, and then I'll equate them to be 1, right? And then I'll have one more equation. Okay, so I have the same number of equations that I started with because I introduced one more and I eliminated one, right? Next is select a working variable and express all the other variables in terms of the working variable, right? So you'll have to select a working variable and express all the other variables in terms of it. Now you have all the variables in terms of the working variable, so you can solve for the working variable using the normalization property. Okay, and then final thing is to find the stationary distribution by substituting the values of the working variable. So now finally you substitute the value that you have got for the working variable and you'll get your stationary distribution, whatever it is. Okay, so that's how you find the stationary distribution of a Markov chain. Okay, so now we'll be discussing a few properties relating to the stationary distribution of a Markov chain. Okay, and the first property is that a Markov chain with a finite state space has at least one stationary distribution. Okay, what that means is that if a Markov chain has a state space which is finite, that is the number of states are limited, okay, then it definitely has one stationary distribution, at least one stationary distribution, where if it enters it won't be able to exit. Okay, so it will settle down there, right? So any Markov chain with a finite state space has at least one stationary distribution. The contrary example here is of a simple random walk without boundaries. If there is a simple random walk without boundaries, we cannot know if it has a stationary distribution or not, because for a simple random walk without boundaries, the state space, it is infinite. Okay, so if it has an infinite state space, then we cannot know whether there is a stationary distribution or not. But if the state space is finite, that means at least one stationary distribution exists. Okay, so before discussing the next rule, I would like to discuss a property of a Markov chain with you that is called as irreducibility. Okay, and what irreducibility means is that if every state can be reached from every other state eventually, the Markov chain is said to be irreducible. Okay, let's see what this means. Okay, so let's take an example here. Let's say a Markov chain has 4 states and the transition diagram looks somewhat like this. Okay, okay, so let's say this is our Markov chain and we want to check whether it is irreducible or not. Okay, so for irreducibility to happen, or for a Markov chain to be irreducible, every state should be connected to every other state. Okay, so I should be able to go from every state to every other state. So I'll have to check using the transition diagram for every state that whether that state is eventually connected to every other state or not, and that if I am in that particular state, can I reach every other state or not. Okay, so can I transition from 1 to 2, 3 and 4? That's the first thing I'm checking. Okay, so from 1 to 2 I can go, from 1 to 4 I can go because I can first transition from 1 to 2 and then from 2 to 4, and then from 1 to 3 I can go again because I can transition from 1 to 2, then 2 to 4 and 4 to 3. Okay, so from 1 I can go to every other state, and that is true. Okay, now let's check for state number 2. Okay, because it would have to be true for every state here, that is only when the Markov chain would be irreducible. So we need to check for every state. Okay, and it should be connected to every other state. So for 2, from 2 I can go to 4, I can go to 3 because 2 then 4 and then from 4 I can go to 3, right? So I can transition from 2 to 3 and 2 to 4, but I cannot transition from 2 to 1 since there is no arrow going from here to here. So 2 is not connected to 1 eventually. I cannot reach from 2 to 1. Therefore, this Markov chain is not irreducible. That is, it is reducible. Okay, it's not irreducible. That's our conclusion. So for this sort of a Markov chain which is irreducible, there is a property relating to this. Okay, that's our rule 2. That an irreducible Markov chain has a unique stationary distribution. So if my Markov chain is irreducible, the stationary distribution would be unique. That is, there would be only one stationary distribution wherein I can go and I'll settle down. The Markov chain will go and it will settle down, and there are no other stationary distributions, only one for an irreducible Markov chain. Okay, let's try to see what this means. So let's take an example question, and the question says that is the following process irreducible. They have given us this transition matrix and we want to check whether this process is irreducible or not. Okay, so this process has 4 states and let's call them 0, 1, 2 and 3, and in order to check whether the process is irreducible or not, we would need the transition diagram. Okay, so let's draw the transition diagram. So let's look at this. So a transition from 0 to 0 can occur with a probability of 1 by 3, right? That's what is shown by this. And a transition from 0 to 2 can occur with a probability of 2 by 3. Okay, so this transition is possible, and from 1 a transition to 0 is possible with the probability of 1 by 10. 1 to 1 is 1 by 5. 1 to 2 is 3 by 5. And 1 to 3 is 1 by 10. All right, and then for state 2, if we see, from 2 to 1 is half, from 2 to 1 is half, from 2 to 2 itself is 1 by 3, and from 2 to 3 is 1 by 6. Okay, so these are the transitions that we have. And then from 3 to 1, okay, this transition, or from 3 to 0, that's the first transition, that is given by 1 by 4. From 3 to 1, this transition is given with the probability 1 by 4, and the transition from 3 to 2, that is this one, would be given by the probability half. Everything else is 0. Okay, so this is my transition diagram. Although I did not need to write the probabilities here in order to check whether the process is irreducible or not, but I've done it anyway. Okay, because I just need to see the arrows and see whether I can move from every state to every other state or not. Okay, so let's start checking. Okay, so if I'm in state 0, okay, if I want to go from 0 to any other state, let's check if I can go or not. Okay, so I can go from 0 to 1, can I? I can go from first 0 to 2, and then I can go from 2 to 1. Okay, so that transition is possible. From 0 to 2, I can go directly. From 0 to 3, I can first go to 2 and then go to 3. Okay, so that is also possible. Then let's check for state number 1. I can go from 1 to 0, I can go from 1 to 2, and I can go from 1 to 3 by first going from 1 to 2 and then going from 2 to 3. Okay, so from 1 I can go to any other state. Let's check for state 2. So for 2 I can go to 1, I can go to 3. Okay, how will I go to 0? I'll go from 2 to 1 and then I'll go from 1 to 0, right? So that is also possible. Now for state 3, I can go from 3 to 2, I can go from 3 to 0, and I can go from 3 to 1. So all these transitions are possible, and thus I can go from any state to any other state, and the Markov chain is irreducible. And this means that it has a unique stationary distribution. Okay, so whatever stationary distribution we will find would be unique. Okay, and there would not be multiple stationary distribution. Let's take another example now. Okay, so the next example question is this one, and this again asks us the chain given by the following transition matrix, and is it irreducible? That is what we want to check here. All right, so let's do that. So let's draw the transition diagram. I've got 5 states, 0, 1, 2, 3, 4 and 5. Okay, so let's do that. So I've got 0, I've got 1, I've got 2, I've got 3 and I've got 4. Okay, so I've got 5 states here. Now let's see how the transitions are going. So for 0, I can go from 0 to 0 itself with a probability of half, and from 0 to 1 with a probability of half. Now for 1, I can go from 1 to 0 with a probability of 1 by 3. And I can go from 1 to 1 itself with a probability of 2 by 3. Now for the third one, now these are the states, I see them, this is my transition diagram. Now for 2, I can only return back to itself with a probability of 1. For 3 and 4, I can go from 3 to 3 itself with a probability of 2 by 3, and I can go to 4 with a probability of half. Similarly, from 4, I can return back to 3 with a probability of half, and I can go from 4 to 4 with a probability of half. Now if you see this Markov chain, this is not irreducible, and the reason I say that this is not irreducible is that there is no way of transitioning from 0 or 1 to any of the other 3 states. So you cannot transition from 0 to 2, you cannot transition from 0 to 3, and you cannot transition from 0 to 4, right? That is not at all possible. And then similarly for 1, you cannot make transitions, and if you're stuck in 2, you're stuck in 2, and if the process starts in 3 or 4, it keeps on jumping between 3 and 4. So this chain is not irreducible. Okay, this is a reducible Markov chain. And what I mean by the word reducible is that it can be reduced into 3 different Markov chains. If you see the transition diagram carefully, this process can be divided into 3 different Markov chains. Okay, this is the first one, this is the second one, and this is the third one. And if you will check, it will have 3 different stationary distributions. If you compute the stationary distributions of this Markov chain, it will eventually have 3 different distributions, 3 different stationary distributions. So let's just try to find out the stationary distributions of this process. Okay, this is the given transition matrix, and let's try to compute the stationary distribution. So that would be given by the equation pi p is equal to pi, right? That is stationary distribution is 1, which returns back to itself. Okay, now where pi would be equal to pi 0, comma pi 1, comma pi 2, comma pi 3 and pi 4. Okay, so this would be my distribution, and now let's just see how we'll compute the stationary distribution. So multiplying pi p with pi, I'll get a few equations which would be equal to half pi 0 plus half pi 1 is equal to plus 1 by 3 pi 1. Half pi 0 plus 1 by 3 pi 1, if I'm multiplying them, I'll get these equations, is equal to pi 0, and half pi 0 plus 2 by 3 pi 1 is equal to pi 1. Okay, this is equation number 1, this is equation number 2. Let's see all the other equations. So if we try to see the other equations, the third one would be, if I check it, it would be pi 2 is equal to pi 2, and the fourth one would come out to be 2 by 3 pi 3 plus 1 by 3 pi 4 is equal to pi 3, and the last one would be equal to 1 by 3 pi 3 plus 1 by 2 pi 4 is equal to pi 4. This is the fifth equation that we have. Alright, now let's just try to solve all of these equations and apply the normalization property, which would be pi 0 plus pi 1 plus pi 2 plus pi 3 plus pi 4 is equal to 1. Okay, so if I solve the first two equations here, and this would imply that 1 by 3 pi 1 is equal to half pi 0, right, which would imply that pi 0 is equal to 2 by 3 pi 1. This is from the first equation, and from the second equation I have again 1 by 3 pi 1 is equal to half pi 0. Okay, so these equations are just the same, so I need to eliminate one, and from the first equation I get this form of a thing, that pi 0 3 times pi 0 is equal to 2 times pi 1. Okay, so this is something I know now. Okay, and the first and the second equations are exactly the same, so I need to eliminate one. From the second one you cannot even get a value of pi 2. Okay, this has to be this will definitely be equal to, if pi 2 is if pi 2 is equal to pi 2, it can take any value, right? So in any case pi 2 would be equal to pi 2, right? So it can take any value. This one would be in this ratio, and the last two, if I see, again they are a repetition of each other. Okay, they lead to the same result, so I'm just eliminating one and keeping one, which would give you that 2 by 3 pi 3 would be equal to 1 by 3 pi 3 would be equal to 1 by 3 pi 4, which would imply that pi 3 is equal to pi 4. So these would be any two quantities in the ratio of 1:1. Okay, and all of them have to add up to 1, right? All of them have to add up to 1. So if I have to express them in terms of a working variable, I'll have to write that if these two are in the ratio of 3:2, I can write them as 3a and 2a. Okay, so 3a and 2a can be the ratio of these two. So if pi 0 is equal to 2a, pi 1 would be equal to 3a, right? Because these two have to be in this ratio. This pi 2 can take any value, so let's call that any value as b, and then for the last one, it can take up any value such that these two values are in the ratio of 1:1. Okay, so 2a plus 3a plus b plus these two values, let's call them c, will be equal to 1. Okay, so this has to be true. So we know that this entire thing has to be equal to 1, right? So my value for the stationary distribution, that is pi, would now be 2a comma 3a, that is the value of pi 1, comma b comma c, and this entire thing has to add up to 1. So I'm going to divide this by this factor 2a plus 3a plus b plus 2c. Okay, so that would be 5a plus b plus 2c, right? So 5a plus b plus 2c, if you'll divide this entire vector by this function, then you'll get these values such that all of them will add up to 1 always, right? So that has to be true. So this would be my stationary distribution, and it can be true for any values of a, b and c, right? So it will be true for any values of a, b and c such that this property holds good, right? So now this has many stationary distributions and not just a unique one, and that is something we need to note here. Okay, so and if you look at the Markov chain that represented this, if you look at the Markov chain that we had here, so the Markov chain somewhat looked like this, and we can clearly see that there would be multiple stationary distribution in different segments. We can have different stationary distributions. So if you are in state 1 or 2, if a particular process starts in state 0 or 1, right, then it will have a stationary distribution here, and it will keep on getting values here itself, right? It won't leave this space. If some process is in 2, it will stay in 2, and if some process is in state number 3 or 4, it will continue to stay here, and thus it will have a stationary distribution here itself. So we can have multiple stationary distributions here, and that is something you need to note. So for a unique stationary distribution, the process has to be irreducible. Okay, now let's move on to the next rule. Okay, so before discussing the next rule, I need to discuss with you a new property relating to Markov chains. And what I'm gonna discuss is period of a state. Okay, so what do I mean by the period of a state? So any state I is said to have a period of d. Okay, any state I is said to have a period of d, that is, this d is some constant. If the return to I is only possible after integer multiple of d steps. Okay, so let's just see what this means. Okay, any state I is said to have a period of d, which is a constant, if the return to I is only possible after the integer multiple of d steps, right? Let's just try to see what this means. Okay, okay, so let's take 3 examples. This is example number 1, this is 2, and this is 3. Okay, and let's say if in the first example we have a process which is given by a transition matrix 0.8, 0.2, 1 and 0. Okay, let's say this is the transition matrix. Okay, so the transition diagram would look somewhat like this. For state 0, it going back to state 0 is 0.8, and going to 1 the probability is 0.2. From 1 to 0 it is again 1. Okay, now the definition said that period of a state, okay, period of any state is d if return to that state is only possible after integer multiple of d steps. Okay, so if the return is possible to the state only after 2, 4, 6, 8, 10, 12, so on and so forth, all the multiple of 2 steps, right, the period of that state is equal to 2. Okay, because the return is only possible after every 2 steps, that is after integer multiple of 2 steps. Let's see in this case what would be the period of both the states. So for state 0 and for state 1, let's try to see the period. Okay, so return to 0 is possible, let's say it's possible at 0 steps, I mean 1 step, you'll have to take 1 step. If you are in 0, you can come back to 0 in the next step as well. Okay, so it can be possible in 1 step, and it can be possible in 2 steps, since if you are in 0, you can be in 0 in the next step, and you can be in a 0 in the next step as well. Okay, so 1, 2, and then you can be back in 3 and 4 and 5 and so on and so forth, right? So the return is possible after any number of steps, right? So there is no integer multiple of this. The integer multiple of all of this would be 1, right? We just have to check the HCF. I have to check the HCF, that is the highest common factor. Okay, so the return can be made in every step almost. Okay, that is what it's saying. So this state 0, it is the period of this is 1. Such a state which has a period of 1 is also called as aperiodic. That is, it does not have any period of greater than 1, right? That means that return to it is possible after any number of steps, right? And not just only integer multiple of some steps. Okay, now let's just see for state 1. So if you are in state 1, you'll go to state 2, that is 1 step, and then to come back to state 1 will take you another step, okay? So first return is possible after 2 steps, okay? And then if you are in 1 and you want to come back to 1, you can do it in 3 steps as well. First you'll go from 1 to 0. Then in the next step you'll stay in 0 itself and then come back to 1. So it's possible in 3 steps. It is not possible in 1 step because there is no arrow coming back from 1 to 1. So it is possible after 2 step, 3 steps. Is it possible after 4 steps? Yes, it is. If you are in 1, you can go from 1 to 0 and then you can stay in 0 for 1 step, stay in 0 for another step and then come back to 1. Okay, so that would be 4, 5, 6. Now again the HCF of all of these is the period, which is just 1, right? Because there is no common factor of all of these constants, right? So the period is 1. So this is again aperiodic. Right? So this was our first example and both the states were aperiodic. And when both the states of a Markov chain or all of the states of a Markov chain are aperiodic, the Markov chain is said to be aperiodic. So I can write that the Markov chain is aperiodic. Okay, let us take the next example. Let's consider this Markov chain that is given by this transition diagram. So 0 and 1, okay, again the same steps, and the probability of going from 0 to 1 is 1 and from 1 to 0 is 1 again. Okay, so for this return to 1 is possible after, let's see, and let's check for both the states. Let's check for state 0 and state 1. Okay, so for 0, I can go from 0 to 1 and then come back from 1 to 0. So it's possible in 2 steps. I can go from 0 to 1, then come back from 1 to 0, then go again to 1 and then come back again to 0, right? So it's possible in 4 steps, 6 steps, 8 steps, so on and so forth. It is not possible in 3 steps because it's not, okay? Because if you'll go from 0 to 1, it will take you another step for coming back from 1 to 0, right? And then if you again go from 0 to 1, you cannot come back in 0 without taking a step. Okay, so it's basically possible in only integer multiple of 2 steps, right? So here the period is 2, which is the HCF of all of these. Okay, so HCF or the period is equal to 2. So return is only possible in integer multiple of 2 steps, right? So the period is 2. Similarly for 1, the period would be the same, 2, 4, 6, 8, so on and so forth, because I can go from 1 to 0 and then come back in 1 step, that is 2 steps, 4 steps, 6 steps, 8 steps, so on and so forth. So the period is 2. So here the Markov chain is not aperiodic, right? Let's check for another example. Let's say you have 5 states. Zero, 1, 2, 3, 4 and 5. Okay. And all these probabilities are 1. Okay, so for this Markov chain, return to any of the states is only possible after the integer multiple of 5 steps. So let's check for step 0. So you can be back in 1 going from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 0 again. So it would be in 5 steps. Then again if you go, it can be in 10 steps, 15 steps, so on and so forth, right? So the period here would be the HCF of all of these, the highest common factor, that would be 5, right? You should remember that we do not care about if these steps here, if you check, if these steps were 2, 3, 4, 5, 6, 7 and 8, that does not matter because still the period is 1 because there is no common factor of these, right? But here there is a period because their factor is 5. So for all of these states, if you will check, the period would be 5 and thus the period of the entire Markov chain is 5, right? So it's not aperiodic. Okay, so these were a few examples in order to judge whether a Markov chain is periodic or aperiodic. Okay, let's check a few more. Okay, so let's take a note of a few things. A state with a period of 1 or a state which is not periodic is called as aperiodic. We have already discussed this. Okay, a state which does not have a period is aperiodic. A Markov chain is aperiodic if all its states are aperiodic, right? So if a Markov chain has all of the states in which return is possible after any number of steps, then the entire Markov chain is called as aperiodic. Okay, a state which has an arrow back to itself will definitely be periodic. Okay, if any of the states in the transition diagram has an arrow back to itself, it will definitely be aperiodic because you can come back to it after any number of steps, right? Just how we saw in this example. If you see this one carefully, the first one, okay, here 0 has an arrow back to itself, so you can go come in 0 after any number of steps. So 0, 1, 2, 3, 4, 5, 6, 7, 8, whatever number of steps you want to come back to it in. Okay, so a state which has a arrow back to itself is always aperiodic. For a Markov chain which is irreducible, if any of the Markov chains are irreducible, the period of all the states is the same. Okay, if a Markov chain is irreducible, the periods of all the states will always be the same. Okay, and this means that if one of the states is aperiodic for a irreducible Markov chain, that means irreducible Markov chain is one in which all the states are connected to each other and can be eventually reached from one another. If one of the states is aperiodic, then all of the states will be aperiodic, which would mean that the Markov chain will be aperiodic. And the reason for this is this can be demonstrated again in the same example. This one, see, since the period of state 0 was equal to 1 here, thus the period of state 1 was also equal to 1, because you could stay in state 0 for any number of steps you want, okay, and then go back to 1. Okay, so you can be in 1 and then you can go to 0 and then come back to 1 in 2 steps, then you can go from 1 to 0 and then stay in 0 for 1 step and then come back to 1. Okay, then you can stay in 0 for 2 steps, stay in 0 for 3 steps, stay in 0 for 4 steps, so on and so forth, right? So this means that if any of the states is, and this is because state 1 is connected to state 0. Okay, so this is an irreducible Markov chain, that is you can reach from 1 to 0 and 0 to 1 anytime, okay, eventually. So this means that for an irreducible Markov chain, the period of all the states will always be the same. Okay, and that is something you need to note. Okay, and this brings me to my rule number 3. Okay, this brings me to my rule number 3. We have already discussed that if a Markov chain has a finite state space, then it has at least one stationary distribution. Okay, and if a Markov chain is irreducible, it has a unique stationary distribution. Now the question is, when will this Markov chain settle down in its stationary distribution. That is, when will it attain the stationary distribution? Okay. The rule 3 defines that if a irreducible Markov chain, if you have a irreducible Markov chain that is with a unique stationary distribution, and such a Markov chain is aperiodic, it will settle down in its stationary distribution in the long run. Okay, so in the long run, this process, this Markov chain will settle down in its stationary distribution if it is aperiodic. Okay, and we'll see about the logic behind this in a bit, but then you need to understand that if a Markov chain is aperiodic, it will always settle down in its stationary distribution in the long run. Okay, so what I can conclude from here is that if you have a Markov chain, you can draw this diagram. If you have a Markov chain, it can either have a finite state space, right, let's call it finite S, and you can have one with infinite state space. Okay, this one has at least one stationary distribution. This one may or may not have a stationary distribution. We don't know for sure. Okay, may or may not. Okay, now if this Markov chain, which has at least one stationary distribution, is also irreducible, then that stationary distribution is unique. Okay, so that means it has a unique S, and if it can be reduced, that is, it is reducible into different Markov chains, then there will be multiple stationary distributions. Okay, so I can write it as unique stationary distribution, and this will have multiple stationary distributions. Now, if this Markov chain, which has a unique stationary distribution, it can either be aperiodic or it can be periodic. If it is aperiodic, then in the long run, it will settle down or attain its stationary distribution. We'll do the logic behind this in a very short while. Okay, but you need to note this diagram that these are all the possible cases. Thus, a finite Markov chain with a finite state space, which is irreducible and is aperiodic, has a unique stationary distribution and settles down in it in the long run. Formally, this can be written in this way, that limit n tends to infinity, Pijn is equal to pi j. That is, in the long run, the probability matrix or the transition matrix, all these probabilities of transition from state I to j in n steps when n tends to infinity. N tends to infinity means the long run, okay, in very large number of steps. When the Markov chain has operated for a long period of time, it will tend to settle in its stationary distribution. Okay, so it will become stationary. Okay, and once it has entered its stationary distribution, it will tend to stay there, because we have already discussed that if a Markov chain attains its stationary distribution at time t, it will continue to be in its stationary distribution forever. Okay, so these are a few things that you must note down. Now let's just understand the logic behind why this Markov chain settles in its stationary distribution in the long run only when it is aperiodic and not when it is periodic. Okay, now let's try to see the difference between a periodic and an aperiodic Markov chain, and why a Markov chain only settles into its stationary distribution when it is aperiodic, sorry. Okay, so this is the aperiodic case and this is the periodic case. Okay, so let's try to compare these two. Okay, So we'll assume some starting distribution, and we will see that where the Markov chain is heading in the long run, that is after a lot of steps, okay, and how is it tending towards its stationary distribution. So this is the periodic case and this is the aperiodic case, and let's assume that the starting distribution is 0.9, 0.1. That is the Markov, when the Markov chain starts, 90% of the values are in 0.9 in state 0, and 10% of the values are in state 1. Okay, so you can think about this as the NCD model and think about these two states. So 90% of the people start in the 0th state, and 10% of the people start in the first state, right? Or a policy holder has a 90% probability of starting in the first in the 0th state and 0.1 probability of starting in the first state. Okay, now I'm taking the same starting distribution, that is x0, and trying to compute all the subsequent distributions. So x1 becomes x0 into p. Okay, so this becomes 0.9, 0.1 into 0, 1, 1, 0. This is a periodic Markov chain with a period of 2, because if you see the transition diagram, we have already seen the transition diagram for this one. There are only two states, 0 and 1, and you can get from 0 to 1 with the probability of 1 and from 1 to 0 with the probability of 1. So you'll get from 0 to 1 and then 1 to 0, right? And if I check the period, the time, the number of steps I take of returning to 1 would be, first if I want to return, I would go from 1 to 0 and then back to 1. So 2, then I can take 4, then I can take 6 steps, so on and so forth. So the period would be 2, right? So the period of this Markov chain is 2. All right. So that is my period for this Markov chain, and thus this is periodic. And then here I have the aperiodic case, wherein the transition diagram looks somewhat like this: 0 to 1, and you have got 0.5, and you have got 0.5, and you have got 0.5 and 0.5. So if now this is aperiodic because I can return from 0 to 0 in any number of steps. So 0, 1, 2, 3, 4, 5, 6, so on and so forth, and I can return from 1 to 1 in any number of steps. So this is aperiodic, right? So now let's just see what's happening in the long run. Okay, so x1 would come out to be, the distribution for x1 would now be, if I multiply these two, so this becomes 0.1 and the other one it becomes 0.9, right? So if I multiply them, this is the distribution. And then let's see for x2. So for x2 the distribution would become x1 into p, which would be equal to, if I multiply this with this matrix again, it becomes 0.9 and 0.1. Right, 0.9 and 0.1. And then x3 becomes, if I try to check it, x2 into p, which would be multiplying x2 with p. Okay, so 0.9 and 0.1 multiplied by this matrix right here. So this would come out to be 0.1 and 0.9. So you can basically see that the policy holders or the number of people are shifting from state 0 to state 1 every time, and all the policy holders, if they start with 0.9 here and 0.1 here, in the next time they will have 0.9 here and 0.1 here, and so on and so forth, right? So they will keep on rotating and they will not settle down anywhere. Okay, so this Markov chain is not settling down to its stationary distribution, because every time it's changing, every time the same distribution is coming back again, and the policy holders in the long run, I cannot say that some of the policy holders would be in state 0 and the others will be in state 1. I cannot say that in long run right here. So I cannot tell if I check in the long run how many policyholders will be in state 0 and how many will be in state 1. Okay, because every time the distribution keeps on changing. Okay, and it's not heading anywhere. It's not heading towards its stationary distribution. Whereas if I see in this case, so x1 would be equal to x0 into p here. So that would become 0.9, 0.1 into 0.5, 0.5, 0.5 and 0.5, which would become, if I check this, it becomes 0.9 into 0.5 is 0.45 plus 0.1 into 0.5 is 0.05. So these two add up to 0.50. Okay, 0.50, and the other one 0.9 into 0.5 is again and 0.45 plus 0.1 into 0.5 is 0.505. So they add up to 0.5 comma 0.5. Okay, in this step. Now let's just see the next step. So x2 would come out to be x1 into p. So x1 is this, so it becomes 0.5, 0.5 multiplied by 0.5, 0.5, 0.5 and 0.5, right? So this would come out to be 0.5 into 0.5 is 0.25, and again 0.5 into 0.5 is 0.25. So both of them will come out to be 0.5 and 0.5. So it continues to be the same distribution. Okay, it settled down to its stationary distribution only in one step. Okay, in one step itself we got the stationary distribution, and now this will remain the same every time. Every time you will get this distribution. Okay, so in the long run we can say 50% of the policyholders are in state 0 and 50% of the policyholders are in state 1. Okay, and that is why I can say that for a aperiodic Markov chain, in the long run, people or the Markov chain, it settles down into its stationary distribution. Okay, so that is something I can conclude here. Here see the distribution now after this at all times it will remain same, but here it's changing every time. Okay, so it basically depends on the proportion of people I start with. Okay, here it depends on the proportion of people I start with, and here it does not. Here eventually it will always come out to be this thing, right? Here it will always be 0.5 and 0.5. Here it will depend on how many people started in state 0 and how many people started in state 1. Okay, so that is why I can say that if a Markov chain has is aperiodic, it settles down into its stationary distribution in the long run. Now let's just take a few questions from the revision notes or the past exam questions in order to conclude this topic.